So we have our basic molecular dynamics simulation here with 3 atoms all interacting. And in this video, we're going to expand this to have more atoms and also to have a temperature slider. So to start, I'm just going to add a slider over here. I'm going to call it num atoms. I'll have it go from 2 to, let's say, 20. And over here, instead of creating 3 atoms, we'll create num atoms. I'm going to get rid of these 2. And to start, we'll just have them move forward by a random amount. So now we've got a bunch of atoms. They're all here. I'm going to give them the same color, since they're all the same. And if we run this, we're going to see things sort of blow up. The velocities get super high. And the reason for that is we have a bunch of atoms that are super close to each other. And based on the Leonard-Jones potential, that means they're exerting an extremely large force on each other. And so they sort of go crazy and just start, the velocities get super high. And so what we want to do is make sure that they're not super close to each other. So instead of moving forward random 5, I'm going to write a procedure called remove overlap. And each atom is going to run this when they get created. And the way this is going to work, I'm going to say while overlapping, and I haven't defined overlapping yet, I'll define that in a second. But while we're overlapping, set xy to be a random x core and a random y core. So what this is doing is just saying, if I'm overlapping, move to a random spot. And the way we'll define overlapping is to report if there are any other turtles in a radius of 1. And 1 is important because less than 1 is where the Leonard-Jones force, given the parameters that we have, equals 0. Sorry, it doesn't equal 0. It's where the energy equals 0. The force is repulsive there, but it's not so repulsive. And so if we're closer than that, we're gonna move away. So now when we click setup, we'll see that now there are no atoms overlapping. If you want to see this in action, actually, you can switch the updates to continuous and slow this down. And you'll see the atoms get created, the turtles get created, and then they're changing their shape and color to blue in a circle, and then moving around to random spots in the world. Okay. So now we can run this, and we've already set up our code over here so that each time through, each turtle calculates the net force from all the other turtles. And so this just works. We can have lots of atoms here. As long as we set them up so they're not too close together, everything is fine. And we get this nice molecular dynamics simulation with a lot of atoms interacting. I'm going to go ahead and get rid of this graph because it's not very informative at this point. And the next thing I'm going to do is add a temperature slider to show how we can simulate a system with a constant temperature. So I'm adding another slider here. I'm going to call it temp. We'll go from 0.1 to 8. These units are pretty arbitrary. They're just based on the Leonard-Jones potential. And if we wanted these to be realistic values, we would have to put some constants in here to make things realistic with the measurement system we use in the real world. So this is an arbitrary value, but it will function as a temperature. Okay, so the first thing I'm going to do with the temperature is instead of starting everything with velocity of 0, we're going to initiate the velocity. I'm going to write a procedure called init velocity, and it's going to initialize the velocity based on the temperature. So we know from statistical mechanics that the average velocity is proportional to the square root of the temperature. And there's some constants in here. So the Boltzmann constant, again, this is going to be arbitrary here. I'm going to add a global here called KB, and I'm not going to make this, I'll put it down here for now with the temperature. We're not doing anything here to make this realistic. It's just some number that makes things work pretty well here. So I'm going to make it 1 divided by 10. We typically also have a constant here based on the dimensions of the system. So I'll just put that here for completeness. And then we're going to have, I'm going to make a random number between 0 and 1. in order to split this average velocity in the x direction and y direction. So I'm going to set the Vx to be the square root of a times V average squared. We're squaring it and taking the square root based on Pythagorean's theorem to make sure everything is scaled correctly. And then for Vy, we're going to take V average squared minus Vx squared and take the square root of that. So again, this is just Pythagorean's theorem. So if we have the Pythagorean theorem, Vx and Vy are the sides of the triangle, V average is the hypotenuse, and so this divides things up in those two directions. Okay, we don't need that anymore. And okay, so now when we set this up, we should now not have zero velocity, but it looks like we are still starting with zero velocity. Oh, right. So we're initiating the velocity here, but right now KB is getting set afterwards. So KB is 0, and so this is all being set to 0. So we actually need to set KB above, and I'll move this here too. So we'll set our constants above where we create the atoms in case any of the procedures the atoms run depend on those constants like they do here. So now when we set up, it looks like there's another bug. They're all initiating with a velocity in the same direction. And that is because these are always positive. We don't want them to always be positive. So I'm going to add another thing here where we multiply by, I'm going to call it pos or neg for positive or negative. And that's just going to be a reporter that is going to either report a positive one or a negative one, so that these can be either positive or negative. And we'll do that with an if-else value. So if an if-else value, you give it a condition, and then if it's true, it gives one value. If it's false, it gives another value. So our condition is going to be random2 equals 0. Random2 gives me a random integer between 0 and 2, not including 2. So basically it just gives me a 0 or a 1. It's like flipping a coin. So if it's equal to 0, we'll give a negative 1, and if it's equal to 1, otherwise we'll give a positive 1. And now these initial velocities should be, in different directions. They're not all moving in the same direction. If we set this temperature super low, then we basically start with 0 velocity, and they'll start attracting each other. If we set it high, then they're starting with some initial velocity, and they still go and attract each other. So this is just setting the initial velocity. If we change the temperature while it runs, it's not doing anything here. For that, we need to scale the velocities while the simulation is running. So I'm going to write a procedure here called scale velocities. And what we're going to do here is we're going to calculate the temperature, which again is based on the average velocity of the atoms. So we're going to calculate the actual temperature of this system based on the current velocity of all the atoms. We're going to compare it to what we want the temperature to be as defined by this slider. And if the temperature of the actual system is lower, we're going to speed things up to make it closer to the actual temperature. And if the actual temperature is higher, we're going to slow things down. So we're going to have a scale factor, which is going to be related to the intended temperature divided by the current temperature. And I'll show how to calculate this in a second. And then we know that velocities are related to the square root of the temperature. So the scale factor is going to be the square root of this ratio. And then we're going to ask all of our turtles to set Vx to be Vx times the scale factor and set Vy to be Vy times the scale factor. So if our intended temperature is higher than the current temperature, which I haven't yet shown how to calculate, then this will be greater than 1, and the square root of anything greater than 1 will also be greater than 1, and so it'll speed things up. If the intended temperature is lower, then this fraction will be less than 1, the square root of that will be less than 1, and we're going to slow things down. Okay, so now all we need is to report the current temperature. And we're going to have some constants out in front again, similar to a knit velocity. And then we're going to multiply by the mean velocity of the turtles. And so this is the square because the temperature is related to the square of the velocities. Here we're taking the square root to get back from a temperature to a velocity. Here we're squaring the velocity to get to the temperature. Okay, and so now, let's speed this up a little. We have all these things moving around at a high temperature, and if we bring our temperature down really low, we're going to see them all slow down and they'll solidify into these crystal structures. If we bring it back up, then we're going to increase the temperature, increase a bunch of motion, and we get a higher velocity of all of our atoms. And that is the basics of our molecular dynamics, including both how to do it with keeping a constant temperature. To get molecular dynamic simulations to work at large scale and in various more complicated situations than this, there's lots of details for how to get molecular dynamics to work in various situations. But this video series has given the basics of how it works. And so you should be able, after this, if you understood these videos, to at least conceptually understand what's going on in molecular dynamics. Basically, to summarize it, we have a bunch of objects that we're modeling as Newtonian point masses. So they have a mass, they have a position, and they have a velocity. At each time step, they calculate the forces they're feeling from surrounding atoms. Add up all those forces, they use that to calculate the acceleration, which is how much to update their velocity. And then based on their velocity, they update their position, and they just repeat that over and over. And that is the basics of molecular dynamics.